right, here we go. Good morning. Let's dive right in, like I like to do. I just got to adjust my monitor settings here. Okay, good. Let's see. Oh, got to switch over to my screen here. There we go. All right, so where were we? When we left off, we were working on, we had just finished up the function declarations, right? That's up here. So the next thing to do is our function calls. And we were able to define a function here. We could see the function name. This function doesn't do much. I guess let me make a slightly more complicated function and see if we can actually see what that looks like. So if I just say fun foo a b c, I don't know, for var x is equal to a, x is less than b, x plus equals x plus c, print x. I don't know. That seems like a reasonably complex function. Kafka, hello, good morning. How are you? I've been missing a lot of Chael's streams. She hasn't been streaming recently a lot either, so hopefully she's doing well. Coming along nicely, right? So to speak. All right, so this foo, yeah, we have three. So get local 0, get local 3, get local 1. And then we check to see less. Oh, okay, so yeah, so this is the A, right? And then local 3 is going to be 3 is going to be the X, right? And 1 is going to be B. Okay, yeah, and then there's the less than operator. She's doing good. Excellent. Or you're doing good. Both are excellent. And then, oh, that's right. We still have this bug here where when the script itself doesn't have a name and we need to print out the name for that. So let me take a look at that real quick. Because that's a small little bug we need to address. And this is in the VM, right? Because this is the execution. Oh no, that's the definition. And then the execution starts here, where we define the function itself. You haven't caught any shells. Yeah, I don't know. She's been pretty quiet, and not surprisingly so. I did see her Mother's Day post. That was nice. Right. So in the compiler, when we print out the resulting script, which is where fn compile. Here we go. At the end compiler, that's where we do it, right? If it doesn't have a name, yeah. So I'm just grabbing the current function's name, and this is where we need to actually see, does the current function have have no name? So we can do that here. Let's do that. I'm going to put a brace here so that I only have to have one config featured, and let name equals if, oh, this is annoying because I have to do this whole thing, is empty. Right? If it's empty, then we're going to say script else. I probably have to use toString on that. Otherwise, we do the same exact thing. Like that, probably toString, like that, probably, and then we can say disassemble, and then just give it a name. Does that work? Oh, and I forgot to close something here. This all shifts over like that, and then closes. There we go. Semicolon. Yeah, so this doesn't. This creates a temporary which is freed while still in use, which means I have to do that. And can I do that? And then just put an ampersand on name. Oh no, this. So this I have to clone. Yeah, that's annoying, but that works. All right, so now if I do the same exact thing, we should actually see the angle bracket script there. Yeah. Okay. Good. So let's commit that, and then we'll work on function calls. Good. Add source. Git commit. Print script for function name top level. Good. All right. So function calls. By the end of this section, we'll start to see some interesting behavior. The next step is calling functions. We don't usually think of it this way, but a function call expression is kind of an infix open paren operator. You have a high precedence expression on the left for the thing being called, usually just a single identifier, right? Then the paren in the middle, open paren in the middle, followed by the argument expressions separated by commas and a final closed paren to wrap it up at the end. That grammatical perspective explains how to hook the syntax into our parsing table. So it's kind of, you need this little bit of insight in order to see how to parse this thing properly, right? Because we're going to do, say, foo 1, 2, 3 at some point, and we'll get, so there's an infix of this operator. So it's a foo followed by the operator this, followed by arguments. I guess I space it out a little bit more. Followed by arguments 1, 2, 3, and then a closed paren to mark the end of the function call. So yeah, infix is weird. Infix open paren is weird, but it makes the compiler easy to deal with, I guess. So that means we need to change our left paren rule, which is right here. And I'm going to change it to this, parse, because we have to change all of them now. So prefix becomes this. Infix becomes a new thing called call, which I guess we're going to write soon. And then precedence is going to be precedence call. And we can take a look at where the precedence is in the order of precedence tables up here somewhere. So call is near the top. So call has a higher precedence than unary, for example. So that means if we say minus foo AB, the foo happens first. This open paren happens first. The open paren precedence happens before the unary does, which makes sense because you'd want to have the result of the foo on the stack to negate it. Okay. So, here's call. So that's awfully short. I'm going to put it after binary. Okay. Fn call. And this is just, I have this underscore thing because some of them take this can assign argument, but we don't use the can assign argument in most of them. So it's unfortunate. You can see them all in all the other ones. That was a hack to get something else to work, and I forget what now. Arg count equals argument list, and then self emit bytes. So we have a new opcode called call, and arg count. So that's interesting. The call opcode doesn't take the function to call. The call opcode says how many arguments there are in the call. So how does that going to work then? The parser encounters left parenthesis following expression. It dispatches a new parser function, right? We've already consumed the open paren token. So next we compile the arguments using a second argument list helper. I guess we'll use that also for other things, right? That function returns the number of arguments it compiled, right? Because we're going to have methods eventually, so argument list is going to be helpful there. Each argument expression generates code that leaves its value on the stack in preparation for the call. Oh, I see. So we're going to compile now each one of the argument lists, and we're going to push them onto the stack. And then the call opcode says how many... Okay. After that, we emit a new opcall instruction to evoke the function using the argument count as an operand. So this bit compiles the expressions that pushes onto the stack, And then we have this call saying how many items just got pushed onto the stack. Okay, that makes sense. All right, define variable. It's right here. So after define variable, we're going to add argument list. And it doesn't take any arguments, and it returns U8 for the number of arguments it did create. So we have let arg count is 0. Okay, here's another do while loop, which we're going to make into a loop break loop, I guess. Oh, this is going to have to be mutable, right? Because we're going to modify it here. So if not self check token type, right paren, loop self expression arg count plus equals 1, and then if not self is match token type comma break. It's a little more awkward this way than the do while, but it accomplishes the same job, right? So if we're not matching a comma, then we break out of this argument loop. If it does match the comma, then we keep going in and parse the next expression. So then we're going to self-consume a right paren okay, and then return the argument count like that. Oh no, this consume goes after the if, because we always want to consume the right. We always want to consume the right paren. So, oh right, yeah, we haven't done the opcode call. Oh, that's the only error right now. Okay, that's good. So that's argument list. This code should look familiar from JLox. We chew through arguments as long as we find commas after each expression. Once we run out, we consume the final closing parenthesis, and we're done. Well, almost. Back in JLox, we added a compile time check that you don't pass more than 255 arguments to call. At that time, I said that was because CLox would need a similar limit, and now you can see why. Since we stuff the argument count into a bytecode as a single byte operand, we can only go up to 255. We need to verify that in this compiler too. All right, so we're going to say if arg count self error all right, and we checked for exactly equal to 255, so we only print this error one time, because otherwise if somebody put in 1,000 arguments, you'd see this thing 1,000 minus 255 times if we checked for greater than or equal to. All right. That's the front end. Let's skip over to the back end with a quick stop in the middle to declare the new instruction. All right, so this is still the issue where we don't have opcode. So we'll jump over to opcode and put a call. And then at the bottom, we have to make sure we can decode it. Okay, that's something we have in our Rust thing, so we can switch back and forth between U8s and opcodes. All right, so before we get to implementation, we should think about what the stack looks like at the point of a call and what we need to do from there. When we reach the call instruction, we have already executed the expression for the function being called, followed by its arguments. So our program looks like this. If we pause the VM right on the op call instruction for that call to sum, the stack looks like the script, the for, the sum. So the function does get pushed onto the stack. Okay. 5, 6, 7. Picture this from the perspective of sum itself. When the compiler compiled sum, it automatically allocated slot 0. Okay, right, for itself. And then after that, it allocated slots for the parameters A, B, and C in order. We can actually take a look at where the compiler does that. So the very first thing it does is it takes up the very first slot in the locals array for the function. So this is something that's needed in the VM side of things. Then it allocates A, B, and C. To perform the call to sum, we need a call frame initialized with the function being called and a region of stack slots that it can use. Then we need to collect the arguments passed to the function and get them into the corresponding slots for the parameters. When the VM starts executing the body of sum, we want its stack window to look like this. Do you notice how the argument slots that the caller sets up and the parameter slots the callee needs are both exactly in the right order? How convenient. I'm sure it was more deliberate than convenient. This is no coincidence. When I talked about each call frame having its own window into the stack, I never said those windows must be disjoint. There's nothing preventing us from overlapping them like this. Okay, yeah. The top of the caller stack contains the function being called followed by the arguments in order. We know the caller doesn't have any other slots above those in use because any temporaries needed when evaluating argument expressions have been discarded by now. The bottom of the callee stack overlaps so that the parameter slots exactly line up with where the argument values already live. Different bytecode VMs in real CPU architectures have different calling conventions, which is a specific mechanism they use to pass arguments, store the return address, etc. The mechanism I use here is based on Lewis Clean Fast Virtual Machine. I mean, this makes sense, right? This means we don't need to do any work to bind an argument to a parameter. There's no copying values between slots or across environments. The arguments are already exactly where they need to be. It's hard to beat that for performance. Time to implement the call instruction. All right, so in op call, I think if I try to compile now, oh, that's right, we have this. Let me put in a temporary placeholder for the disassembler. And this needs to return a usize, which is, well, I'll just put offset here for now, and then we'll come back to that. There we go. Okay, so now in here, opcode call. So the first thing we're going to do is get the arg count. And then we're going to call value peak arg count arg count. So call value is a new function we're going to create. And return a bool apparently. This might not work because we might be borrowing this mute and this borrowing an unmute, immute. So we might have to rearrange this. Return error, interpret result, runtime error. Otherwise break. We already have a break. So this might be an issue. Yeah, we don't have call value and we don't have... What's this complaint about? Mismatched types. Oh, I have to make this a usize. Okay. All right, so let's write call value. Oh, we have to pop a frame here. We need to know the function being called and the number of arguments passed to it. So peak or arg count is the function being called. On the stack, right? So we have, this is already on the stack. If we do this, so what we're doing is pulling it off the stack. Not pulling it off the stack, but we're probably making a copy of it. No, we're passing back a reference. Yeah, see, this is an immutable reference to this, and then call value is probably going to need to be mutable. Because we're going to be modifying things. And runtime error definitely mutates because we set the has error flag. So we're going to have to do this a different way. We want to be able to do a call value, callee. And then this happens just before the break, which is going to pop the frame. This says frame is frame count -1. So it just gets the address. So it's just setting the current frame to the current frame -1. Okay. Which means get the last frame, which we already have a function for, I believe. Let's just double check that on frames here. We have a frames push. Yeah. So IP gets the IP address of the last one, and we already have a current frame. So we don't need to worry about this line here, because we can always get the current frame just by calling this function. My question is, what are we doing here? And I think we might be able to get away with, because we store the current frame, the current function, which I believe is what we're trying to pass in here, as just an index into the stack. I should make that a note, right? Yeah. So we might be able to just say use argcount to determine where on the stack this lives. So let's try to see if that works. Call value. So instead of doing that, we can just pass an argcount, and that'll tell us it'll tell us how many arguments there are, but it'll also tell us where in the stack the function lives. All right. We need to know the function we called and the number of arguments passed to it. We get the ladder from the instructions operand. That also tells us where to find the function on the stack by counting past the argument slots from the top of the stack. Right. We hand that data off to a separate call value function. If that returns false, it means the call caused some sort of runtime error. When that happens, we abort the interpreter. All right, so instead of passing a reference into the stack here, I'm going to see if I can get it down here and work it that way. If call value is successful, there will be a new frame on the call frame stack for the called function. The run function has its own cached pointer to the current frame, so we need to update that. Oh, I see. Yeah, so this we don't need to do because we can, like I said before, we can always get the last call frame. Since the bytecode dispatch loop reads from the frame variable, when the VM goes to execute the next instruction, it will read the IP from the newly called function's call frame and jump to its code. The work for executing that call begins here. Okay. Yeah, so if we look here, self read byte gets the current, whatever the current frame is. It gets the chunk from, I think chunk also does that, right? Yes, it also gets the current frame. This should be, I bet you we can get away with this, right? Okay, let's try this. So this is after peak. Call value. And we said this has to be mutable because we're reporting a runtime error. And then we're going to say argcount use size. And it's going to return a bool. Okay, so we're going to say is object callee. So our callee is going to be whatever's on the stack minus right. We can just do that. To get the callee. Where do we create the new frame? Oh, we create the new frame down here. Okay. So we can do match callee. If it's a value of function f, func f, right? Then we can say self call f, which is an RC, right? Can I do this? No, I probably can't, right? Because I need the, well, let's try it. Self call f and the argcount. Otherwise, oh, and then this returns true. Oh, it just returns what the result of call is, okay? Otherwise, it's going to return false. Oh, I see. Let result equals this, and then we can say if not, let's say success. If not success, then we're going to say if runtime error can only call functions and classes. Oops. Too many C's, not enough C's and too many S's. Okay. So now we still have this self call to write. But there's another error. What's the other error? Oh, this? Okay. All right. There's more going on here than just initializing a new call frame. Because locks is dynamically typed, there's nothing to prevent a user from writing bad code like this. If that happens, the runtime needs to safely report an error and halt. So first thing we do is check the type of the value, right? Okay, that's what we're doing here. Otherwise, the actual call happens here. All right, so now we're about to find out what type this is. This might be a reference to an RC. Okay, let's find out. Call, not self. It takes the function, which is I think this, if I remember correctly, and then arg count is going to be our old friend usize, and it returns a bool as well. So we're going to just generate a call frame and return true. That's all we're doing. We're actually pushing the call frame. So let's see how we push call frames. It's up here. Let's copy that and splat it up here. Okay, so function is the address of on the stack, the index into the stack. So that's self stack len minus arg count, maybe. IP is going to be in 0 again, and then slots is going to be stack top minus arg count minus 1. Oh, here it is. So it's the same as function then. Which means that this probably is -1, right? So do we just... If they're the same, then we can get rid of one of them. Let's see if this works. First thing we do is check the type of the value we're trying to call. If it's not a function, we are out. Otherwise, the actual call happens here. This simply initializes the next call frame on the stack. It stores the pointer to the function being called and points the frame's IP to the beginning of the function's bytecode. Finally, it sets up the slots pointer to give the frame its window into the stack. The arithmetic there ensures that the arguments already on the stack line up with the function's parameters. The funny little -1 is to account for a stack slot 0, which the compiler set aside for when we add methods later. Okay, parameters start at slot 1, so we make the window start at 1 slot earlier to line them with the arguments. So this just returns true. I guess that's going to change soon. Before we move on, let's add a new instruction to our disassembler. Right, so we didn't do that part. Let's do this. Ooh, no function here. Oh, there's no this isn't an RC? Oh, I thought I made this an RC. It's just a function. Okay. Why did I think I made that an RC? Maybe I was thinking about doing that. Okay, cannot borrow self as mutable because it's already borrowed as immutable. Oh. Yeah, so this is the issue I was talking about before. Is that now callee is a this callee is a value like that, right? Yeah. And so now we're using data extracted from here. Maybe that's why I was thinking it had to be an RC, because we need to be able to reference it here. We'd just be able to say RC clone F like that, probably like that. So let's make that, get rid of that. Let's make it an RC. Which means what has to change? RC new. Interpret. RC new, I guess, there. Oh, that's interesting. I can pull it out as a function. I didn't know you could do that. I thought you had to put an RC here. Both of those work. That's interesting. And we're not even using this parameter because it was going to go in here. Huh. Okay. Kafka says, I think you changed the semantics a little of call value. Well, let's see, what are the warnings? Maybe that'll help point me in the right direction. Yeah, so func isn't used. This is saying warning can't borrow self as mutable because it's already borrows is mutable, and his borrowing pattern is not meant to be accepted and may become a hard error in the future. So we should fix that. And this has a result that must be used. Really? Huh. Okay. Yeah, okay, so we definitely need to fix this. Kafka says you're calling runtime error both when the call returns false and when it isn't a func. Yeah, because right now call, let's see what they do here. Oh, I see. You're right. You're right. Let's just return that. I mean, this should just be a matches right now, but okay, we'll do it this way. Thanks, Kafka. So I'm still bothered by this because we need to. I'm saying clone the RC, but it's still saying I'm doing a mutable borrow on. Maybe if I get rid of all this business. I think you need the ampersand on that one there. Oh, you don't. But it's still a bug. We don't actually need it right now, right? So why am I still even doing this? Right? Because it's on the stack. And now there might be in the future there might be a thing where it's not on the stack. Because right now our function's on the stack, and it might be the case that we're going to put an object on the stack, in which case we're going to have everything's going to break. We still have 3 warnings. Oh, because we're not using function anymore. And then on 2.11, we don't need that. Okay. I wonder if this will work. Let's fix the disassembler. It's just self byte instruction call offset. And then one more quick side trip. Now we've had a handy function for initiating a call frame. We may as well use it to set up our first frame for executing the top level code. Okay, so that's back in our VM. Interpret. So that's saying here, instead of doing all this stuff, we'll push the function and then say self call 0. I think that's what they're saying here. It compiles. Let me grab this little fun function here. And see if we can call it. Ooh. Okay. Huh. I didn't have a print in there? Oh, I did. I'm not seeing it though. Here's the call. Here's the get locals less. Oh, it was less already. X is less than B. Yeah. What did I do wrong here? 0, 1, and 2 for A, B, and C. So A is 0, X equals 0, X is less than 1. It is. X equals X plus 2. So we should have gotten at least print a 1, but I don't see that. 0, 0, 1, 2. We call. We get local 0. And we're in function foo. Oh, wait a minute. Why is that appearing more than once here? Did we forget to do something? Here it's doing 2 is less than 0, and 2 is not less than 0, so that's false. Yeah, something's wrong. Something's not working right. So I'm calling foo, so it's pushing foo on the stack. It's pushing the 3 parameters onto the stack. And then it does a call. And this ends up this here. I'm not sure that this is correct. But then X gets assigned 2. And then we check to see if 2 is less than 0. Do I have that less than wrong? Var A equals 2 is less than 0. That should be false, right? Print A. False. Huh. Yeah, something's gone bizarre here. I think there's some stuff on the stack that doesn't belong. Why is that? Why is this here? Okay, so there must be something I'm not... Maybe it's because we haven't finished this yet. Maybe there's still more work to do. I'm just getting ahead of myself here. Okay. All right, so we modified this, and then in our VM, we're going to change this call. We're going to check the function's arity. Oh, that's right. The function's arity contains how many arguments there are. So if we look at function, we do have arity right here. I guess what we can do is just make a little helper function here. Pub fun arity check self arity use size bool arity equals self arity, right? And then we can just call that from the VM. So after we push the frame, before we push the frame, we check the function there. See, now we need the function. go away. We need the function now, but the function is right there, right? So we can actually get it from here again. And now we know that it's a func let value func call e is equal to this, right? And we can say call e, and then here we're going to return false. So this needs to say if call e dot arity check, is that what I called it? Arg count. If it doesn't check, then we're going to do a runtime error. Self runtime error. Expected arity arguments, but got arg count, comma. Oh, this has to be in a format. And then we just put in call e. Oh, I guess we do need the arity value. So might as well do it like this then. Not equal to arg count. Return false. And then else panic, tried to call a non-function. That shouldn't happen. I think that's all we need to do there. And then we're going to need to write this function here called arity. Format bang. And then inside function, we're going to just change this to arity. And change this to a usize. And get rid of this. And just return self arity. Just a basic getter. Okay, so we have 3 warnings. Oh, this is, again, we're doing this mutable borrow, immutable borrow business. I guess we could reorder the code. Let arity matches equals this, and then we can just say call e arity equals arg count, else panic. And then these lines come down here. Oops, stop it. And this becomes if not arity matches, like that. Oh, so we need that value. So we can just do this. And then we can just say if arity equal arg count, arity and then I messed up a something. Oh, this here. 2 warnings. Result that must be used. See that? Where else do I use? Oh, just return. Okay. Yeah, but in this call function here, we don't have that. So I'll just have to say, throw it away. There. Okay. So that checks the arity. So we should be able to actually test, right? Let me grab this function again. Cargo run. define the function, and then I should be able to fail calling it if I just give it no arguments, and it panicked on line 139. Okay, let's take a look. Yeah, see, we're I don't like what's going on here. Oh, because slots. Yeah, we must not be... It's calling the foo without... Here's the call. Right? And then we have... Right away we have get local. So it looks like the arity check didn't work. Let's just print that out. Println arity equals arity and arg count equals arg count. We should be getting here, right? Oops. Oh. How come it's not getting the... Oh, we're probably not setting the arity anywhere. That's probably, where would that be? Here's where we compile the arguments. Yeah, we should be... Where did I mess that up? Oh, here we go. So we should be setting the arity here. Okay, let's find out what this looks like in compiler. So that must be where the bug is. Compiler. Oh, it's in function. We are incrementing the arity. And we're supposed to be setting this function with it an arity here. Println. I'm going to make this debuggable, I guess. And then we're going to have to add... Oh, it already has debug. Okay, good. Let's find out what it's doing. Here's the function, and arity is set to 0. So that means if I try with the wrong arity here, yeah, expected 0 arguments but got 1. Okay, so the arity check is working. But this value should not be this. Here's the code, and it's all on line 1. So why is... Well, yeah, that was something we never looked at yesterday when we added that code, inc arity. And that's here. Result borrow arity. Println look up arity. Self arity borrow. Okay. Of course I did. Of course I did. Okay. Looking up arity equals 0. Okay. That means we're not incrementing it correctly. Let's print that out. increment to arity 1, 2, 3. And then when we go to get it, oh wait, did I pull it out? Did I make a stupid error here? Let me delete these lines because we know these are working. Oh yeah, look at that. Oops. How come I can't make this window bigger? Okay, here we go. So what's happening is I'm swapping out results with the previous compiler, and then I'm pulling it here, which is dumb. That was dumb. So we need to pull it beforehand. Let arity equals this. Go away. And then we'll just put arity in here. Here. Okay. And let's see if that works. Cargo run. Put that there. Oop. Of course I did. Put that there. Oh, I got to delete that. Looking up arity equals 3. That's good. Incremented arity. Oh. I thought I deleted those lines. I didn't. Don't need function equals func. That's the eprintln. That's fine. And then over in VM, we can get rid of those. Oh, that's just the run. That's the print opcode. We don't need that. Binary op. Why was I doing this one? Oh, that's debug output. Okay. So let's see. Does this work? It does. Does it compile? It does. Does it work? So if I say foo this way now, expected 3 arguments but got 0. If I give it too many, 3 arguments but got 4. It still doesn't work because we have this weird business with the double stack here. I'm not sure what's going on. And then when we're done, we still have this stuff on the stack, so that's not good. So there's probably some popping we need to do. All right, so where were we? After all of that, I think we got that bug fixed. Runtime error checking, so we just did this, and then we have a Stack Overflow. Okay, there's another error we need to report that's less to do with the user's foolishness than our own. Because the call frame array has a fixed size, we need to ensure a deep call chain doesn't overflow it. We don't have that issue because we have a vec, but I don't mind putting in a limit here for call frames. This says VM frame count is frames max, which I think is 256. So let's just throw that in there. Before we push. If self frames len. Ooh, I might have to say self frames bar len maybe. Is equal to 256. Like that. Let underscore equals self runtime error stack overflow return false. And yeah, actually, instead of all this return false business, we should be returning a interpret result so that we can just use the same runtime error thing. Okay. And then we have printing stack traces. While we're on the subject of runtime errors, let's spend a little time making them more useful. Stopping on a runtime error is important to prevent the VM from crashing and burning in some ill-defined way, but simply aborting doesn't help the user fix their code that caused the error. The classic tool to aid debugging runtime failures is a stack trace, a printout of each function that was still executing when the program died, and where the execution was at the point it died. Now that we have a call stack and we've conveniently stored each function's name, we can show that entire stack when a runtime error disrupts the harmony of the user's existence. It looks like this. All right, I'm just going to scan forward. Really, here we go. Returning from function. Yeah, we haven't done any of this pop business. Okay, very good, very good. I was still nervous about that whole thing getting messed up, but all right. So this is in runtime error, replacing 4 lines. Although that doesn't really mean anything to us. What are we actually doing? This looks like the end of this message, maybe. And then reset stack is here, so maybe we're just replacing this one line here with a backwards walk through the call frames. So can I just iter rev on that? So we have the frames here in a vec. So can I just say for frame in self frames iter rev? The instruction is going to be the IP that we have, and then we're going to get the line of that instruction from the function itself. So the function, so let's do this one step at a time here. Function is going to be self stack of frame.function. Let me see if that works. No. Move occurs. Can I do that? Yes. Okay. So that's a reference now. So now we're going to say let instruction. Let's use the same variable names that they have. Stop it. Instruction is equal to the frame's IP address. And I don't think we need to do this business here. We do need to subtract 1 maybe, but we're not pointing into the code. We're just getting the IP directly of that function. So that would be self stack. Oh no, frame. Yep. Dot IP -1. Oh, that's not. Yeah, that's the instruction. And then we have in chunk. There must be a way to get the line. Right, because the chunk contains the lines. So let's take a look at where lines are. When we write, we push the line. Get line. Okay. And we just pass in the IP. So we can just say ePrintln. Oh, just ePrint. Line. Well, let's get the line this way. Let line is equal to the function get chunk, I think, right? And dot get line IP. So it's that. In space, and then if function name is null, then we'll say script, or we're going to say the foo. So function dot, let's take a look at what options we have under function in terms of getting the name. Actually, we should just have this return the name. Pub fun stack name self, and return a string. I guess a references now, a string. Let's see if we can do that, and then we'll say if self.name is empty, like that. We can return, maybe this should be stir script, or self name as stir. That's probably going to say borrowed is mute, or temporary was created or something like that. So function dot stack. No, we just print function dot stack name. Right, that's why we wrote it, so we could do it. 1. Okay, let's see what blows up. 4. Oh, instruction. You can't subtract. Oh, it's a ref cell, so borrow. And get chunk is not in. Oh, function is a value. We need to destructure it. Is this going to even work? Else panic. Try to get a stack trace of a non-function. And if that happens, we'll have to debug it in a better way. Ooh, that compiled. All right, so now if we do this, it should print this out. Let's find out. Put that there, cargo run, broken. It almost worked. Line 4 in C, line 2 in B, line 1 in A, line 7 in script, and then we have the line 4 in script. 1, 2, 3, 4. Yeah, so we have this extra something or other going on here. Why is too many showing up over here? Oh, that's here. Okay, yeah, duh. So it says expected 0 arguments, but got 2, which is what we wanted to see. But of course, what's bugging me is the fact that we have this extra line 4 in script coming out. So there, obviously I'm pushing one too many stack frames or something. Let's look for call frame. So here I push one, right, when we do the call, but that should be the only time we push a call frame. That gets the current frame. Yeah. This is the only place we ever push a call frame. And if we look for the function call, interpret, it's here. For the script, we push the script onto the stack. And then here, we push this, whatever function we're calling onto the stack. Oh, duh. Okay. That's where that came from. Let's try again. There we go. All right. So we have it all correct. There's some disagreement on which order stack frames should be shown in a trace. Most put the innermost function at the first line and work their way towards the bottom of the stack. Python prints them out in the opposite order, so reading from the top to bottom tells you how your program got to where it is. The last line is where the error actually occurred. There's a logic to that style. It ensures you can always see the innermost function even if the stack trace is too long to fit on one screen. On the other hand, the inverted pyramid from journalism tells us we should put the most important information first in a block of text. In a stack trace, that's the function where the error actually occurred. Most other language implementations do that. Yeah, this is like the key, right? Some message scrolls off the screen. You can see, you can work your way up how you got there. Whereas with this, you'd have to scroll back and say, okay, how did I get the error? This seems like a handy. Anyway, returning from functions. Yeah, so okay, we're getting close. We can call functions and the VM will execute them, but we can't return from them yet. We've had an op return instruction for quite some time, but it's always had some kind of temporary code hanging out in it just to get us out of the bytecode loop. The time has arrived for a real implementation. All right, so let's take a look at what they're doing here before we implement it in Rust. So this is in run, we have opcode return. It just says return OK. So we're going to replace this with, we're going to pop the result. We're going to decrement the frame count. So that's easy enough. We can just pop the frame. If we're at the top, then we pop the last value off the stack and return OK. Otherwise, we reset the stack top to however many slots there were in the frame, push the result, and then grab the new frame. The heck? So what's the difference between frame count? Oh, this is the stack, right? And it's getting the frame slots for the stack top. When a function returns a value, that value will be on top of the stack. We're about to discard the call function's entire stack window, so we pop that return value off and hang on to it. Here. Oh, I see. So we're going to pop off the result, right? We're going to reset the stack top to remove all of the frame. Okay, then we discard the call frame for the returning function. That's this line. If that was the very last call frame, it means we finished executing top-level code. The entire program is done, so we pop the main script function from the stack and then exit the interpreter. Otherwise, we discard all of the slots the callee was using for its parameters and local variables. That includes the same slots the caller used to pass the arguments. Now that the call is done, the caller doesn't need them anymore. This means the top of the stack ends up right at the beginning of the returning function's stack window. We push the return value back onto the stack at that new lower location. Then we update the run function's cached pointer to the current frame, right? We don't have to do that. Just like when we began the call on the next instruction of the bytecode dispatch loop, the VM will read the IP of that frame and execution will jump back to the caller right where it left off, immediately after the op call instruction. This part I don't quite get, though. We're setting the stack top to the frame slots. Isn't the frame slots just the number of slots in that particular frame? Oh, but it's pointer. So we actually what we need to do is pop slots off of the stack in order to get this to work. So I think, okay, so let result equals self hop. If, let's take a look here. We have call frame stuff in the VM. We can say call frame.push. We'd have to say call frame.pop, right? So self frames pop. And we discard the value. If self frames is empty, then we're going to do an additional pop and return OK. Okay. Otherwise, we have to decrement the size of the stack by slots in the current frame. Let slots equals self current frame. Let's take a look what that function returns. It should just be the frame. Oh, we just popped that off. Previous frame. So we have the now we have the previous frame, and what we want to do is remove n from the stack. We want to remove n. So how do we pop n? Rust vec pop n. Saturating sub. All right. So we can truncate it to slots. Self stack truncate self stack len minus prev frame slots. I have no idea if that's correct. We might have to do a -1 or a +1 or something like that. Yeah. Okay. Let's see how close we get with that. And now we're going to push the result back on. Self stack push result. And current frame is already set. We don't have to worry about that. We don't have to do a break statement. Okay, so let's see what blows up. Boom. Oh, that's an option call frame, so I need to unwrap it. Ooh. And the warning is, oh, we don't need the line number? Oh, right, because we're just printing it here. Okay. Good enough. All right. Epic Blog says off by 1 errors. Yeah, that's my favorite thing about programming. Off by 1 errors. So we'll see. I don't know. I mean, the bug is going to be blaringly obvious, I think, once we get there. Right? So let's try the old for loop that I had before and see if we're even close to getting it right. Cargo run. The bane of off by 1 errors is the they're hard to find, but we know where this one would be if there is one. All right, so 194 we panicked on an option unwrap. So that means, yeah, so we don't have the full backtrace, but we can imagine that we're in the return statement since that's the last opcode that was printed out. Right, we must be in here either on this line here where we do a self pop, or in this line here where we do a self pop. Or I did a self stack pop here back when I saw extra stuff on the thing, and I don't know if this was something I was supposed to do. Aha. So let's do the full backtrace. Oops. Let's do the full backtrace. Yeah, and then see which pop is actually broken. Let me grab this again. And it is 194. Oh yeah, it told us where it was, but it's coming out of VM run 153. So it's this pop here. We got this result here. Let's take a look at the output. Script is on the stack. Huh. So script is on the stack, but that means that that first pop popped the script instead of popping the result. Oh, we didn't do everything here. See, I didn't go all the way. I didn't go all the way here. So what I missed, see, I'm trying this out, right, without even thinking about it. When we do the compiler, if we're emitting a return, we need to emit a nil. That's what, okay, that's what I just read there. Right, so we read this, so this is all makes sense. Note that we assume here that the function did actually return a value, but a function can implicitly return by reaching the end of its body. We need to handle that correctly too. The language is specified to implicitly return nil in that case. To make that happen, we add this. The compiler calls emit return to write an op return instruction at the end of the function body. Now, before that, it emits an instruction to push nil onto the stack. And with that, we have working function calls. They can even take parameters. It almost looks like we know what we're doing here. All right, so let's see if this works now. Let's grab this. Because now it should be able to pop that off. Let's leave the backtrace on. Okay. And I should be able to say foo 1, 2, 3. All right. So it ran the script. It didn't panic, but the script didn't do what it was supposed to do, right? Because we were supposed to print X for in each step through the loop. And we still have this issue that we're getting the wrong parameters. So there might be something going on with the parameters. There might be something going on here with this additional foo. I don't know where that's coming from, because we should have the script, all the arguments, and then here shouldn't be another script, right? We should just be calling call. And then when we say get local 0, oh, get local 0 is getting the function instead of getting a. Ah, that's what the bug is. Let's take a look at get local. Yeah, so I think what's happening here is we're getting the wrong thing. We're getting read byte as usize should be 0 because we're getting the 0th. We're getting in our function. Let me make this a looper. Oh, I used vim instead of vi. Nvim. Not big. Thank you for the follow. Much appreciated. Let's grab this code again. Oh, it's gone, of course. Is it gone forever? No, it's up here. Okay. And this will allow me at least to format it correctly. Like that. Okay. And then now I should be able to say cargo run, looper. And we'll see the whole thing. And we see that it doesn't do anything. Oh, because I didn't call it. Da, foo, 1, 2, 3. Semicolon. All right. So I think, so this get local needs to get the local 0, right, from here, right? So get local 0 is correct. It's getting A. And then get local 3 is going to be X. It's, oh, there's no assignment. Shouldn't the assignment happen first? Cargo run for var a. Did I break that? It was 1, a is less than 3, a equals a plus 1. I need to add in increment, don't I? Print a. No, that works. So let's see what this looks like. Constant, get local, constant, less. Okay. But these... I mean, it's working, right? So that part is definitely working. We're able to get the constant values and get local. So there is no assignment. I guess it just gets it as through the constant. In this case here, we just say get local, and then we compare if it's less right away. Here's where we add and set local 3, right? So that's setting the A to the increment, and pop, and then loop back to 2. I'm surprised that there isn't something has to initialize the X value, doesn't it? And then there's the nil in the return. Okay. Oh, I got to get rid of this line here. I forgot that was in there. Okay. Yeah, so there's a bug here somewhere, and I'm going to have to track this guy down. I don't want to work on return statements until we figured out what's wrong here. Because this is not working. And the other thing I wanted to test was whether or not the return statement is actually popping all the correct stuff off. And I mean, I can't tell if it is. Although so here, op return. Let me print this out because it looks like it popped only one entry off the stack. So maybe slots is wrong. When we create the function, we need to create the number of, this is wrong also, isn't it? How is this even working then? Oh no, that works because we're pulling the result here. Yeah, okay, so that's fine. But where are we setting slots? That's in the call frame. Okay, so maybe that's where things get messed up. VM, event call. So here's where we're setting slots. So println, can I do this? I don't know if call frame has debug, but we can add it. Self frames. If it doesn't, we'll just throw it in there. Yep. Call frame cannot be formatted that way. Let's make it that. Oops. Let's make it that way. Derive debug. Yeah, it's a usize, a ref cell, and a usize. So that's pretty straightforward. So let's see what it looks like. Cargo run looper. Okay, so we can see, yeah, slots is 0, but that's because this is the 0 function. And then here's our new function, and it says slots 1. Huh. I thought the slots were the number of arguments plus the... Where do we use slots? Oh, slots is actually equal to the point on the... Oh. VM stack top minus arg count minus 1. So it's actually the value that we need to set. So we don't do this. We do that. That's what it's saying. I think. Let's try it. So push the nil. It popped all that stuff and it threw the nil on there. Okay. So now this part's working now. All right. But we still have a problem here that it's not getting the correct local values. It's still getting this foo, which is index 1 plus the 0. Oh yeah, that makes sense, right? Because we have... Yeah, so when we grab the local, we need to increment past this thing. right? We have slot offset plus slot. And the slot offset is the number of slots in a current frame. The slot number is this thing, but remember the 0th position is going to be... No, why didn't... This bothers me because why wasn't this... Do we have get local in here? It must be in the previous chapter. No, the previous chapter? No. More? No, this says local variables. So I'm just looking for that opcode. Oh, get underscore local. Okay. So it's saying just the slot, right? And then we had to modify it. So let's take a look up here. It should be get local. Not in that one. Not in that one. There we go. Frame slots slot. Okay, so maybe, and that's what I tried to translate that into. Should the slots be up by 1? No. Yeah, I don't know where slots is pointing. Okay, so let's assume that this is the fix until everything breaks, and then let's try cargo run looper. There we go. It actually ran. I see something got printed. And did everything get popped correctly? It looks like it. Yeah. Let's try it with some better values. So we'll start at 1. We'll go to 19, I guess, and then increment by 3. And I'll run it with the no default. Oh, I still have the call frame printed. But I think that worked, right? Because it incremented by 3s. And it stopped when it got to 19. Okay, so println. There. Okay. All right, so I'm out of time, unfortunately. But we will get to... We did function declarations. Function calls. We just finished function calls. And we're almost done with this chapter, but I don't have time. I can't stream tomorrow, but I can stream on Thursday. And we'll do return statement. I think this is very short. Native functions. This might be a tricky one. Okay, so return statements and native functions for the next stream on Thursday. Let's check in with Clippy. Clippy's happy. Git add source. Git status. Git commit -m. Section 24.5. Function calls. Well done. Okay, git push. And we gotta take a look at it like I always do. Oh, that's the wrong one. That's the wrong one. That's the wrong one. That's the wrong. Oh, did I get rid of it? I thought I had it up here. Nope. Oh, yeah, because I was looking here. Okay, there we go. All right, thanks for hanging out, everyone. Hope you have a great rest of your day, great tomorrow, and I will see you Thursday for return statements and native functions. Take care.